Hi everyone. Through this class, we are going to discuss about equilibrium electrostatics of heterojunctions. Let us consider the electrostatics of the NP heterojunction. As in the case of homojunction, potential differences exist across the space charge region in both the N region and the P region. These potential differences corresponds to the built-in potential barrier on either side of the junction. The built-in potential barrier for this ideal case is defined as shown in figure to be the potential differences across the vacuum level. The built-in potential barrier is the sum of the potential differences across each of the space charge regions. Ideally, the total built-in potential barrier VBI can be found as the difference between the work functions. Therefore, VBI equal to phi SP minus phi SN, where phi SP is the work function in P region and phi SN that in N region. This is the energy band diagram of a narrow band gap and a wide band gap material before contact. And from this figure, the work function in this P region that is equal to sum of this E chi P and the gap between ECP and EFP. And this gap, it is actually EGP minus the gap between EFP and EVP. So, we can write it as E chi P plus EGP minus EFP minus EVP. This is our first term. Then, for this second work function, that is phi Sn, similarly, it is sum of this E chi n plus this gap. This gap is equal to this EGN minus this EFN minus EVN. So, second term, we can write it as E chi n plus EGN minus EFN minus EVN. Then, on rearranging, this EVBI that is equal to this term E chi P minus E chi n. So, it is equal to E into chi P minus chi n plus this EGP minus this EGN. So, it is equal to EGP minus EGN. Then, here it is minus this term that we can take. So, it is equal to plus EFN minus EVN. Then this minus term. So, minus EFP minus EVP. We have already studied that delta EC is E into chi n minus chi P. So, this first term, it is minus delta EC. And EGP minus EGN, that is delta EG. So, we can write the second term as delta EG. And this third term, that is KT into log NVN divided by PNO. And this fourth term, it is KT into log NVP divided by PPO. Here this PNO is the whole concentration in N material, PPO that is the whole concentration in P material. And thus NVN and NVP, they are the effective density state functions in N and P materials respectively. We know that delta EC plus delta EV is delta EG. Therefore, delta EV equal to delta EG minus delta EC. So, this is delta EG minus delta EC. So, EVBI, now we can write it as delta EV plus, Now we can combine two log terms here. Now it is Kt ln PPO divided by PNO into NVN divided by NVP. So this is the expression for built-in potential barrier in terms of valence band shift. Similarly, the expression for built-in potential barrier in terms of conduction band shift, we get like this. EVBI equal to minus delta EC plus KT ln NNO divided by NPO into NCP divided by NCN, where this NPO is the electron concentration in P material and NNO is the electron concentration in N material. Next, we are going to consider the electric field and electric potential in space charge region. For homogeneous doping on each side of the junction, and we consider the N region, electric field is given by En equal to ENDN divided by epsilon N into Xn plus X, where NDN is the donor impurity concentration in N region and epsilon N the permittivity of the N-type material. And this Xn, it is the width of the space charge region in N region, and X lies between minus Xn and 0. And in P region, electric field is given by EP equal to ENAP divided by epsilon P into XP minus X, where this epsilon P is the permittivity of the P-type material and NAP is the acceptor impurity concentration in P region, and XP is the width of the space charge region in P-type material, and X lies between 0 and this XP. En equal to 0 when X equal to minus Xn and this EP equal to 0 when X equal to XP. The electric field density D is continuous across the junction. Therefore, at X equal to 0, epsilon N En is equal to epsilon P EP. From this, we get it as NDN Xn equal to NAP XP. This equation states that the net negative charge in P region is equal to net positive charge in N region, which is the same condition that we had in PN homojunction. From this equation, we can write Xn by XP as NAP divided by NDN. By integrating the electric field through the space charge region, we get electric potential. So, the potential in N region, that is given by VBIN, that is the integral of this equation. So, it is equal to ENDN Xn square divided by 2 epsilon N. Similarly, in P region, the potential, electric potential EVBIP, that is equal to integral of this equation, that is equal to ENAP XP square divided by 2 epsilon P. And the ratio of these potentials, that is VBIN by VBIP, that is equal to epsilon P divided by epsilon N into NDN divided by NAP into Xn square divided by XP square. And we know that Xn by XP is NAP by NDN. So substituting this value, we get this ratio as epsilon P divided by epsilon N into NAP divided by NDN. The total built-in potential barrier is VBI equal to VBIN plus VBIP. So it is equal to E n dn xn square divided by 2 epsilon n plus E nap xp square divided by 2 epsilon p. Substituting xp from xn by xp equal to nap divided by ndn and substituting in this equation and solving, we get the expression for xn like this. Instead of xp, if we put the value of xn from this equation in terms of xp, and if we put that value here, we can solve for xp and we get the expression like this. And total depletion width W equal to xn plus xp, that is equal to 2 epsilon n epsilon p n dn plus nap the whole square vbi divided by E n dn nap into epsilon n n dn plus epsilon p nap whole raised to 1 by 2. This is the total depletion width in zero biasing. We can use all these equations for forward biasing and reverse biasing. For reverse biasing, the VBI we want to replace with VBI plus VR. And for forward biasing, replace VBI with VBI minus VA, where VR is the magnitude of reverse bias voltage and VA the magnitude of forward bias voltage. As in the case of homojunction, a change in depletion width with a change in junction voltage gives junction capacitance. So, for n capital P junction, the junction capacitance Cj prime is equal to E ndn nap epsilon n epsilon p whole divided by 2 into epsilon n n dn plus epsilon p nap into vbi plus vr whole raised to 1 by 2. And plot of 1 by Cj prime the whole square versus Vr is a straight line. As we have already studied, extrapolation of this plot of 1 by Cj prime whole square equal to 0 is used to find the built-in potential barrier VBI.